Welcome back to Differential Calculus. In this video, we're going to be summarizing all of the tools that we've talked about so far this course on analyzing graphs. And there have been a lot of them. We've talked about the axis intercepts. And we talked about asymptotes. To one extent or another, those are ideas that you probably were familiar with coming into the course. We found tools for identifying extrema, the local maximums and minimums. Again, something that you were familiar with coming into the course, but calculus gave us the ability to develop tools for identifying them analytically. With extrema comes regions where the function is increasing or decreasing. We've also talked about concavity and points of inflection. All of these things come together to give us a very interesting picture of the graph of a function. So let me get my head out of the way. Let's take a look at a particular function, a somewhat interesting function. F of x equals 5 minus x raised to the 2/3 power. And we want to see how many of these tools we can use, how many features of the graph we can identify, and see if we can even draw the graph without having to resort to computer software. The y-intercept remains the absolute simplest thing we can find. The y-intercept is the point f of 0. So, 0, 5 is our y-intercept. Continuing with the algebra skills of analyzing a graph, we can look for x-intercepts. X-intercepts are, of course, places where f of x is equal to 0, which means that 5 minus x to the 2/3 power is equal to 0, which means that 5 is equal to x to the 2/3 power, and 5 to the 3/2 power is the value of x. I guess we should probably end up with a plus or minus on that, because we did just take a square root here, even though it's kind of hidden. Analytically, I would call this 5 times the square root of 5, or negative 5 times the square root of 5. But for the purposes of actually drawing a graph, a numerical approximation is going to be much more useful. So I can grab out my calculator and see that these are around 11.2, positive or negative. The next thing I notice is that this function is continuous everywhere. Right? It's not a polynomial because it has this weird fractional power, but the cube root is also continuous everywhere, and the 2/3 power is again the cube root of x squared. So yes, this is a function that's going to be continuous everywhere. We don't have any issues there, which means no jump discontinuities and no vertical asymptotes. And if we take the limit as x goes to positive infinity, we're going to get something that tends towards negative infinity. And if we take the limit as x goes to negative infinity, well, since we're squaring it, it's going to be positive infinity, and then we're taking a negative, which is going to make it a negative infinity. The function is going to go towards negative infinity this way as well. And just with that, we have a decent bit of information about this graph. We know that the function is going to go through the point 5, 0, which is somewhere around here. It's going to do some stuff. I don't know what yet. And then it's going to head towards negative infinity. Somewhere along the line, it's going to cross through the points 11.20 and negative 11.20. That's a lot of information that we have about this function without too much work. But we can do a little bit more work, and we can figure out what's going on in the space between as well. So continuing with our strategy, I don't know, maybe extrema might be nice to analyze. So we have our function, which I'm going to rewrite here just for my convenience. And we can take the derivative of this function, which is going to be negative 2/3 x to the negative 1/3. And critical points are places where this is equal to 0. Divide both sides by negative 2/3. We get that x to the negative 1/3 is equal to 0. And x raised to a power is equal to 0 if and only if x itself is equal to 0. So there is one extreme value. It is the point where x is equal to 0, which we already know is 0, 5, because that was the y-intercept. Interestingly, we can do a lot with that information. Because we know that the function is tending towards negative infinity, we know that it's got to be going downward at the end. And since there's only one extreme point, well, it can't be going upward at any point near. So that point has to be a local maximum. We can, of course, verify that by using either the first derivative test or the second derivative test. Plugging in something bigger than 0, like say positive 1, we get negative 2/3 times 1, which is negative 2/3. The only thing that matters is that it's negative. Plugging in something smaller than 0, like negative 1, we'll get negative 2/3 times negative 1 to the negative 1/3 is still negative 1. So negative 2/3 times negative 1 is positive 2/3. The only thing that matters is that it's positive. So again, first derivative test gives us that we have to have a local maximum at this point. It also gives us the function will be increasing to the left of x equals 0, will be decreasing to the right of x equals 0, which again is what we came up with just thinking about it, but always worthwhile to verify that information. Moving onward, we also want to be able to talk about the concavity, which means we're going to need the second derivative. All right, so we want to differentiate negative 2/3 x to the negative 1/3, which I guess is going to be positive 2/9 times x to the negative 4/3. All right, points of inflection are going to be points where this is equal to 0. Once again, this is x raised to some power equals 0. which is only going to happen when x itself is equal to 0. All right. Some oddities here. In fact, the function is undefined when x is equal to 0 because it has a negative exponent, but undefined works just as well as 0 for critical points and points of inflection. But we will once again sketch out a number line, put our 1 point of inflection on it, test the function to the left and to the right. Plug in positive 1, you get f double prime of 1 is 2/9. The only thing that matters there is that it's positive. Plug in negative 1. Negative 1 to the negative 4/3 power is positive 1. Multiply that by 2/9, so you get a positive number out there. The function is always concave up. That's kind of interesting. The function is always concave up when it is increasing and when it is decreasing. So let's try to bring all of this information together. I've got my critical point, 0, 5. We know that that's the y-intercept. We know that that is the point of inflection. We know that that is the maximum. We've got the x-intercepts. Around 11.20. And around negative 11.20. We know that the function is decreasing but concave up, which might look something like that. And again, decreasing but concave up going over this way, and gives us something like that. In order for this to work out, instead of having a nice smooth curve, we have a sharp point here at the maximum. A sharp point like that is called a cusp. Not terribly important to know, but some interesting vocabulary. The important thing to realize here is that just by thinking about the calculus, thinking about the tools that we have been discussing, we're able to draw the graph, and draw a pretty nice graph if I do say so myself. If I jump over to Desmos, and I've cut off on the screen here where the actual function is named, but this is in fact the function that we've been playing around with, you can see that the graph looks very similar. Desmos gives you some nice options. Right? If you click on the curve, it highlights interesting points like x-intercepts and y-intercepts, so you can get to those values. They give us a little bit more detail than what I did, but it all works out to be about the same. Right? I don't need Desmos when I can do this by hand, but tools like that exist. They take seconds to work through. I guess the last question then is, well, what's the point? Why did I spend the time to go through and do all of this analysis by hand when I can just go on to Desmos, type this thing in, I get the picture, I don't have to do any thought about it? Well, the mathematician's answer is doing it this way gives you exact values. Right? I don't have to stick with the approximation. It is, which way do I go? There it is. It is right behind me here, this negative 11.18. I know that that is exactly negative 5 times the square root of 5. Is that actually helpful? Is that useful? I don't know. But it is something, it exists, we can think about it, and that counts for more than a little. Other than that, though, we can think about this as something we can build on. Right? I don't expect you to be able to do it now. This is kind of more of a skill building thing. But thinking about what some of these features mean. When you look at a graph and you see that it's concave up, understanding the tie to there and the second derivative, looking at a cusp and seeing interesting things that happen with that, being able to tie those features to what the calculus does will then allow you to take those shortcuts in the future. If you need to know qualitatively when the second derivative is positive or negative, you can graph the function, you can analyze that graph, and you can make decisions from there. You can also, at some point, start thinking about this in more abstract terms. What if I have a function where I know some things about x, but I don't have the coefficients, right? I have a minus b times x to the 2/3 power instead of 5 minus x to the 2/3 power. How do the values of a and b change what's going on here? A tool like Desmos can't really help you with that. You have to have a specific special case that you are studying. The analytic tools will allow you to do that more generally. All right. So a couple of reasons why I think it's still worth being able to do this by hand, even though no one is ever going to graph a function by hand. You're going to let computer software do it for you every time. All right. Going back to my note page here, let's wrap up with a problem for you to try. Fairly similar. How about g of x equals x minus 1, the whole thing, raised to the 2/3 power. All right. I'd like you to play around with all of the tools that I've just been talking about, sketch this graph by hand, and then go to Desmos, double check your work, and see that you've gotten the same thing. Take a few minutes to play around with that, and I'll see you in the next video.